Hi, this is Dr. Goldstein, and I am going to be discussing the mean value theorem. So the statement of the mean value theorem is that if you have a continuous function on a closed interval from a to b, and that function is differentiable on the open interval from a to b, then there exists some c between a and b such that f prime of c is equal to f of b minus f of a divided by b minus a. Okay, that was a mouthful, so let's break this down a little bit. Remember that these intervals a to b refer to x values, and so here we are talking about an x value, c. So what we're saying in this formula, okay, again, we have these conditions. Your function has to be continuous and differentiable, so these are just your functions, kind of nice. This f prime of c is the instantaneous rate of change at x equals c, and this expression over here, this f of b minus f of a over b minus a, this is our average change on this entire interval from a less than or equal to x less than or equal to b. So remember that differentiable means that your function has a derivative. And so we're saying that our function has a derivative everywhere from a to b. So for x between a and b. And when we say that our function is continuous, we're saying that it has no jumps, breaks, or skips. So we know that our function needs to be continuous so that we're not skipping any values, and we know that our function needs to be differentiable because we want to know that there is a derivative. So those are the conditions of the mean value theorem, and then what it's telling us is that our instantaneous change at a specific point is going to be equal to our average change on the entire interval. Here's another way of phrasing that. The instantaneous change, this is the slope of the tangent line at x equals c, and then on the other side over here, this average rate of change is the slope of the secant line from x equals a to x equals b. Okay, so these are two different ways of understanding what exactly the conclusion of this theorem is telling us, what exactly we're getting out of this. Let's look at this visually to see a little bit more what this actually means. So here I have a function f of x, and I have one point A, and I have another point B, and I have graphed these points, A, f of A, and b, f of b, on my graph. And what this green line here is, this is the secant line through the points at x equals a and x equals b. And so we can see that the slope of that line is the same as the slope of this red line, and this is our tangent line. This is a tangent line. And these are parallel. They have the same slope. So they have the same slope. And so what we have is that this tangent line at this point C has the same slope as the secant line that goes through the points at x equals a and x equals b. So this is visually what the conclusion of the mean value theorem looks like. This is what f prime of c equals f of b minus f of a over b minus a looks like. So this f prime of c, this is the slope of the tangent line. So it's the slope of that red line. And this f of b minus f of a over b minus a, this is the slope of the secant line. And so again, another way of thinking about this is that your average change over an interval is realized as instantaneous change at a particular point. So at a point. Okay. I'm going to give you a mathematical example, and then I'm going to give you more of an intuitive example to understand why people might find this to be a useful concept. Mathematical example first. Let's look at the function f of x equals 4 minus x squared on the interval from -1 to 3. So first let's check the hypotheses of the theorem. We need our function to be continuous and differentiable. So our function here, f of x equals 4 minus x squared, is continuous because it's a polynomial. And we know that polynomial functions are continuous. And then differentiable, remember differentiable asks, do I have a derivative? And so if I take the derivative of this function, f prime of x is negative 2x, and this always exists. I can plug in whatever x value I want, and I will always have a derivative. So my function is also always differentiable. And so the conclusion of my function, the conclusion of the mean value theorem is this f prime of c equals f of b minus f of a over b minus a. And so in this problem here, our a is -1 and our b is 3. And so we have f of 3 minus f of -1 over 3 minus -1. And we can simplify that. So if I take 3 and I plug it into my function, I have 4 minus 3 squared. Minus, if I take -1 and I plug it into my function, I have 4 minus -1 squared. 3 minus -1 is 4. So here I have 4 minus 9 is -5. Minus, this is going to be 4 minus 1. So this is -5 minus 3 over 4. This is -8 over 4 is -2. So that's the one side of that equation. On the other hand, we know what our derivative is. We already took our derivative. Oh, we did? Yeah, we did. Here's our derivative. There's our derivative right there. So we know that f prime of c, using this formula, this is -2 times c, this is going to be equal to -2x. Oh, hey, this is true when c is 1. And we can see, oh yeah, that's between -1 and 3. So this is an x value that's between our a and our b. So what we knew from the mean value theorem is that some c exists. So the conclusion tells us that x equals c exists such that f prime of c is equal to this quantity -2 that we calculated. It doesn't tell us what c is. In this case, it's easy enough to find it. So this technically down here, this is technically not from the theorem. The theorem just tells us that it exists. So the theorem just says, okay, it exists. And in this case, it's easy enough that we can compute it. We can compute exactly where this average is realized as the instantaneous rate of change. Okay, so that's a computational example. Let's look at more of an intuitive example of what on earth this theorem looks like in the real world. So for example, let's say that we have a 10-mile stretch of road, and it has a speed limit of 65 miles an hour. Now this is enforced by cameras on either end, and they take a picture and record the time that a car drives past them. So let's say that my camera spits out some data and I have a car that starts this 10-mile stretch at 10:02.15. So that's 10 o'clock, 2 minutes and 15 seconds a.m. and ends at 10:09:45 a.m. So all in all, I know that my car takes 7 minutes, 30 seconds to travel this stretch of 10 miles of road. And now we have enough information to say, hey, this guy gets a speeding ticket. So we conclude the car was speeding. Now, you may say, how on earth do we know that? Okay, well, first off, let's consider the position of this car. That's the function that we're dealing with, right? We're dealing with position with its derivative velocity. So here, position is our function, velocity is the derivative. I know that my position is going to be continuous because there's no way that this car can jump from one position to another. It has to go smoothly from one place to another. And then I also know that the velocity is going to exist. I always have a speed. So I always have a derivative, so my function is always differentiable. So the velocity exists. So position is differentiable. So the mean value theorem tells us, we've checked its hypotheses, the mean value theorem tells us is that at some moment, the car was going its average speed. That's what the mean value theorem tells us. And so we can go and compute, well, what was its average speed? Well, it went 10 miles in 7.5 minutes. So this gives us 4/3 miles per minute, which if you multiply by 60 to convert to miles per hour, this turns into 80 miles per hour. So its average speed, the car's average speed for these 10 miles is 80 miles per hour. And the mean value theorem tells us at some point that car was actually going 80 miles per hour. Maybe the car was only going 60 miles per hour at the beginning and the end, but the car sped up in the middle and the average speed was 80 miles per hour. So we can conclude that this car was speeding, and the calculus police can give this car a speeding ticket. So that is the mean value theorem, that as long as you have a continuous and differentiable function, at some point your instantaneous rate of change is equal to your average rate of change.